Una Victor, can you hear me? So it is better now. Faith, let others join. So I will give about 15 minutes grace. Can you people still hear me? So I'm waiting for more people to join. Can you people still hear me? Can you see what is showing? Can you see what is showing? Is it better now? Watch it. Expand it now. Let me even join and see. Let me use another this thing and join and see what the complaint is all about. But I don't understand what you can. Hmm? Can you hear me? Okay, since we are having issue of clarity here, and this is the highest this thing can go. I don't know how I can share it better, but I think I should proceed. We are just 25 minutes late. Last week we solved this question for the series magnetic circuit of figure 11.29 here. Can you see my mouse? Okay. So we solved this question last week, and we were able to. Hold on, I think I used my hand to. We were able to get us. Hmm? So the question is, let's repeat it again. If you can still hear me, let's repeat it. Series magnetic circuit of figure 11, 21, 29. Find the value of current magnetic flux of 4 times 10 raised to power minus. Determine the permeability and the relative permeability for the magnetic condition. So we have the magnetic circuit, which is represented with this symbol here, the symbol of A. This is, we are still learning this process. Just bear with me. Let's move down to the solution. So we have our flux density, which is what we are meant to calculate. The flux density is phi over area, and we have our area to be 2 times 10 raised to power minus 3. I think is here, is written on this, is written here. This is what we are analyzing. Are you seeing figure 11.9? We indicate. So since we have our area, we have the number of turn and the length of this magnetic circuit. The length of the magnetic circuit is 0.16 meter. The number of turn is 400 tons, and the area is 2 times 10 raised to power minus 3 meters square. Our magnetic density is equals to phi over area. This was the formula I gave you last week. And phi here is 4 times 10 raised to power minus 4, and area is 2 times 10 raised to power minus 3. And when you divide them, you will have it to be 2 times 10 raised to power minus 1, which is 0.2 Tesla, or you say is 0.2 Weber per meter square. So for this B that we are looking for in table 11.2, you feel it to be 0.2 Tesla. Then another one is the magnetizing force. The magnetizing force, which is H. And H, because it's a cast iron steel, H is equals to 170 over M. So applying the Ampere-Circuital law, we yield that Ni is equals to H of L. And remember that Ni is equals to force. Ni is equals to force from our previous formula. Ni is equals to force. You can go to the last formulas I gave you. And that force is equals to, if we want to calculate the magnetizing moment, we say that is force per what area. So we now have that Ni, which is force, over Ni, which is force, is equals to HL. Let's go back to the formula of that last week so that you see it clearly. So this is the formula we discussed last week. This is force, which is Ni, and magnetizing force is equals to force per length. You can see it very clearly here. Why I'm just trying to drag is that I can't even get feedback from you. So it's me at all. If I can hear from you that what we are doing, we are proceeding, there would have been a better something. The transmission would have been seamless. But notwithstanding, let's still proceed. So we have this as the magnetizing force, where H is equals to Ni. Remember that last week I told you that force is equals to number of turns times current. And the magnetizing force is number of turns times current all over number of length. So let's go back. So we have our length to be 0.16 meter and number of tons to be 400 tons. So applying it to this circuit, we have that 170, which is the magnetizing force for cast steel, times by length over 400 tons, will give us 68 milliampere. 68 milliampere. I will still copy this thing and send to you on the platform so that you will go through it. Then the permeability of the material, which is B over magnetizing force. B over magnetizing force. So the magnetizing force forecast here is 170, while the magnetic density is 0.2 Tesla. So when you calculate them, you have 1.76 times 10 raised to power minus 3 Weber over the permeability of free space, which is 4 pi times 10 raised to power minus 7. And when you do that, we have 935.8, 935.8. And this material should be ferromagnetic material, because for ferromagnetic material, the relative permeability is above 100. So let's do for this other one. Hilary said that we can't see it. So the next thing we are going to do today, we've solved one question, is to do transformer. And when we talk about transformer uses the principle of electromagnetic induction. And what we know as a transformer is something that can improve the output of an input, something that can make an output to increase or decrease. And what transformer does is that they increase voltage or current. Transformer increases voltage or decreases voltage. Or you can say that transformer can increase voltage or current. But transformer cannot transform power. Transformer cannot transform power. And why do we say that? We are going to do some of the calculations and you understand why a transformer cannot transform power. People should hold on. Let me get some things out. Where's my workbench? So in this transformer, for easy explanation, I'm going to run a simulation with the system and show you what I mean. That a transformer cannot transform power, but it can change the voltage level or the current level of the input. And the principle of this transformer is that it uses magnetic flux, what we've been discussing before. The change in magnetic flux of the input, which is the primary section, and that of the secondary section determine what the voltage level can be. For a transformer, we have coils of wire, like when you turn a wire into tons of wire. When you roll a wire, maybe you can use your biro, you roll a wire, bring them together. There is a magnetic flux existing between that ton of wire. I've explained this thing using the Lenz's law. Okay, Mbafit, transformer increases both voltage and current, and it equally decreases voltage and current. But the way it does it is what we are going to see. I will share this screen for you. Just hold on. This will should hold on. Hmm? I'm trying to run simulation so that we look at it. Are you still with us? Bunuku, transformer cannot transform power. So please, can you see my screen? Can you see my screen? So if you can see this screen now, let me stop the simulation. So what we have here is an AC signal. For those in technology, I draw this symbol and you people were telling me another thing. This is called a voltage source. If you can see my mouse hovering around this V1, it's called a voltage source. And this one, you people were labeling current or diode, is called transformer. And this one is Earthlink. Can you people hear me? If you can hear me, the easiest way is to write on the comment section. Okay. Is the circuit diagram clear for you to see? Is it clear? I think you should increase the imaging quality of your this thing. Huh? Increase the quality, please, for higher resolution so that you can see this. Those of you shouting is not clear. Increase the quality. Go to the setting of that your this thing. Go to setting of your YouTube. Increase the quality, the video quality. Set it to 480p. Let me even write it. Set the video quality. Is it clear now? Chidera Cynthia, is your own clear? Okay. So I think we've overcome some certain hurdles. Since you can see it better now, should I proceed? Okay. So this you are seeing here, let me go back to the circuit. Can you see my mouse? Can you see my mouse? Yes. I'm trying to see if I can be viewing this thing we are doing. Please bear with me. Oh. The screen is no longer sharing. Can you see the shared screen? Okay. Okay. So since you can see it, you can see my mouse. This is what we call voltage source. And this voltage source is AC voltage source. This is 120 volts RMS by 60 Hz frequency. We will still discuss about that frequency. For those of you in Biomed and P&O, we will still get to that part of frequency. Then this is a transformer. And this transformer ratio is 10:1. This side that has 10 is the primary side of the transformer, where the input is fed, the input voltage you need to put to the transformer. And the one with 1 is the secondary side of the transformer, where you take your output. And for this transformer reduces the voltage of the input to 12 volts. So how does it do it? Because of the tons of wire we have here is 10 tons, about 10 tons. And the one we have at the secondary side is 1 ton. I hope you are following me. I hope you people are following me. All right. Okay, since you are following me, that has reduced to 12 volts. And what we need is 12 volts. Take, for instance, we want a 12 volts to power our hand tool. For those of you working with hand tool, the P&O and dental technologies, maybe your hand tool is using 12 volts. You use a transformer to step it down from 120 volts to 12 volts. Or assuming that the input is 220 volts, let's see if we can change the input to 220 volts. 220 volts by 50 Hz. So I've changed it now, and I'm running the simulation. And what we are seeing is what? We are seeing 22 volts. If you are following me, you will say, you indicate. Somebody said that the screen is no longer sharing. I'm not sure about that. Is the screen still sharing in your own side? Even my own is not sharing again. Let me reshare it again. The screen should be sharing by now. Okay, somebody said it's sharing now. So let's proceed. That's what I want to hear. Like I said, before we did for 120 volts, but I changed it to, let's try the 120 volts again. I don't know where the screen stopped sharing, but let's try it again. So because at this primary side, it has 10 tons, secondary side has 1 ton. This transformer is a step-down transformer, which means it's going to reduce this input voltage to a voltage equivalent to this ratio, which is 10:1. That's the output will be 1, while the input will be 10. So if you have about 10 at the output, at the input, what you have at the output will be 1. That's what that indicates. And we run our simulation. You can see that we have a 20 volt RMS volt by 60 Hz frequency at 0 phase angle. At the output, where we connected is our multimeter. This thing is a multimeter, you can see it. We are reading 12 volts, which means the transformer have stepped it down to 12 volts. Is it clear to you? Because I will still write other things. Is it clear to you before we go into the mathematical solutions? Then let me try another one, 220 volts. Let me try 220 volts by 50 Hz. And we run the simulation. We are having 22 volts. We are having a 22 volts. But assuming that this transformer has a ratio of, let's say, 5 is to 5:10. This transformer has a ratio of 5:10. You can see the 5 is at the primary coil 1, while the secondary coil 1 is 10. And we run this simulation using 220 voltage RMS by 50 Hz. And look at what we are going to have. Are you seeing it? What you are having is 400 volts, but it has increased this to almost 240 volts. It has increased this to 440 volts, sorry. But hold on. Assuming we have two here, and we run our simulation. So we are having at the output 1.1 kilovolts, because at the primary side of the transformer we have 2 tons of wire, while at the secondary side we have 10 tons of wire. So these 220 volts we change to 1.1 kilovolts. So this is a step-up transformer. This is a step-up transformer. The screen has stopped showing. The screen has stopped showing. Is the screen sharing now? So if you look at this T1, which is the transformer we are talking about, you have at this primary side, the side you connected this voltage source, which is 220 volts RMS by 50 Hz frequency. We have 2 tons of wire. These 2 here means the number of tons of wire. Then at the secondary side, we have 10 tons of wire. So what we measured using our multimeter will be 1.1 kilovolts, meaning that this transformer is a step-up transformer. Are you following? The transformer is a step-up transformer. Now, there are some formulas and laws guiding this. I think it was, is it Vivian or what that asked something about is not within or whatever. I don't understand the question. But she can repeat that question she asked before. Let me clear her. Vivian, I'm still waiting. Vivian, I'm still waiting for the question. I don't have a problem, sir. I did not say you have a problem. I say you asked a question. Please, I'm trying to see from my phone if there is a question asked. So we are going to proceed. Somebody asks, what principle does he use? Yes, Ogili. Ogili Victor, your question is in the right side. When the primary side is lesser than the secondary side, it is a step-up transformer. When the secondary side is lesser than the primary side, is a step-down transformer. So we did something about induction. We said something about flux. And when we talk about flux during the discussion of magnets, we said that anything within the region of magnetic flux experience the effect of that magnet. And what is that effect? If you bring a metal close to the region of a magnet, that metal will start to behave like a magnet. Are you following me? Now, bring that to the effect of when you turn a coil of wire and the wire start to behave like a magnet. As the wire is behaving like a magnet, around the region of that wire, it will start to have the magnetic flux. And anything placed within that region, we have an induction. The flux of that magnetic coil will induce the other material around that region to behave like that material. Take for instance, what will I use to show you an example? Take for instance this primary side of this transformer that we have here. The primary side, you can see it. Look at the symbol. Please, can you hear me? Those of you asking questions, like the one, I don't know this person, Ion. Who is this Ion? Did you write your reg number to this class? I don't know you. But please, your question is outside the what we are doing. I can attend to that and know your problem later after the class. You can chat me up on the platform. Are you hearing me? So, like I was saying, this is the primary side, the side with 2. The side written 2. This 2 means 2 turns. The wire is turned 2 times. Then the side written 10 is the secondary side. Assuming that this side written 2, you connected this voltage source to it, it will start to behave like a magnet. And as it's behaving like a magnet, if you bring this side that has 10 turns around the region, these 2 turns is going to influence these particular 10 tons to start to act like a magnet. And as it's acting like a magnet, because this one is 2, these 2 tons is going to multiply whatever it has here by 10, and this one at the secondary side is going to multiply. But what is causing all these things is what we call the mutual inductance of a magnet. The mutual inductance of a magnet caused by the magnetizing force of a magnet. The mutual inductance of a magnet. I think I will step down this one and share another screen. So this is a chapter 12 of the material I'm using. I said that for every coil, there is what we call self-inductance, or what we know very well that is a mutual inductance that exists in every coils of material of different dimensions. So the phenomenon of mutual inductance is the basic principle of transformer operation and electrical devices that has electromagnetic principle. Are you following me? So for mutual inductance, look at what I've been discussing here. This is the transformer we are talking about, and this is the voltage source, just like the screen I showed, and I ran some with it. This the one I simulated that I showed you. So you can see this magnetic flux of this coil. Can you see my screen? You can see the magnetic flux of this coil resonating just like a normal magnet. You see how it's moving just like a normal magnet. And this is the primary side embodying the voltage. This is the primary side embodying the voltage source. This N here is the number of turns. N is the number of turns. Now, as this N is increasing, the number of flux around this region is equally increasing. So if we bring a material, be it metal or anything, or a ton of wire around this flux we are seeing, are you following? This will cut across it. This particular flux will cut across it. If as this one is entering the region of this particular primary side flux. Because of this mutual inductance, which is equally a magnetic flux, is going to make this one to start to behave like the primary coil. This primary coil we are seeing. Are you following? Do you understand this principle I'm sharing with you? You can write on the comment section. The screen is blank. The screen is blank. My own is still showing. Let me reshare it again. Who is saying is blank? Confidence. You see. People should stop misleading me. Huh? You should stop misleading me. Oh. Okay. Okuchukwu Paul said I should explain the mutual inductance again. I should explain the mutual inductance. Hold on, I'm coming on. Okay, can you see the screen now? Can you see the screen now? You people are not replying. Can you see the screen now? So somebody said I should re-explain the mutual inductance. This mutual inductance, let me start from the beginning. This is a ton of wire. You can see it. Let me go to this particular distance so that you see my mouse. Can you see my mouse? Okay. This coil of wire, when connected to a voltage source, this is the voltage source. When it's connected to a voltage source, like we've been explained in our electromagnetic principle, start to behave like a magnet. It will start to have magnetic flux, magnetic line of force, like a normal magnet. And from the diagram you are seeing the line of force coming out from the ton of wire. So it's going just like the normal magnet. It goes to left and it goes to right, but it will from the north pole and enter through the south pole. But in this case, it will start from the positive side and enter through the negative side. So as it's moving, this is the flux line. This is the flux line. So anything that is brought close to this region where this flux line is existing is going to behave like this particular ton of wire, just like when you bring something close to a magnet, a permanent magnet, and that permanent magnet influences the material to start behaving like that permanent magnet. So in this case, this secondary ton of wire is brought close to this region. This magnetic flux is brought close to it. And by virtue of this flux line will make this secondary side to start behaving like the primary side. But the ratio is behaving depends on the number of turns, like the number of turns of wire that is having. Who asked that question before now? Somebody said I should re-explain. Let me check the person's name so that I can call it. Okuchukwu Paul, are you following? Okuchukwu Paul, I hope you are following. So, as this thing is happening, it will start to behave like the primary side, but at a ratio of the number of turns it has. Take for instance, I have maybe two marker. Are you getting me? But the amount you can draw from me depends on the number of your strengths. Like the number of marker, since I have about two markers, the number you can take from depends on the strength you have. And that strength you are talking about is this number of turns. So if this primary side is 1 and the secondary side is 2, if we have one voltage at this voltage source connected to the primary side, the output from this secondary side, because it has 2 turns, will be 2 volts. Let's do it again so that you understand what I mean. Let me go back to the simulation. We have 1 turn and we have 2 here. And we have 1 volt. Let me just do it 1 volt. I will share this screen now. I will share this screen. Okuchukwu Paul, I hope you are seeing what I'm going to do. So, can you see it? Can you people see the screen? Okay, it's now up. Okay. So watch. You will see that here, this is the voltage source, and we have 1 volt. Are you seeing the 1 volt? If you are seeing the 1 volt, you say yes. Okay. Now, you see that this primary side of this transformer has 1 turn of wire. This is the one. Let me show you how I did it. This is the primary coil. Number of turns, 1. Secondary coil, number of turns, 2. I hope you are seeing it. So if I run this simulation, if I should run this simulation, we are going to have 2 volts at the output. We are having what? 2 volts. Because at the primary side, we have 1 turn. And we are giving 2. The primary side is 1 volt. But because we have 2 turns of wire at the secondary side is going to multiply this mutual flux by 2, and we have 2 volts. And that is what we are saying by the mutual let me share my mutual flux again. I hope Okuchukwu Paul, you've understood what I mean by that, so that we proceed to other side. Our time is running. So, can you still see my screen? Okay, I'll stop sharing. Can you see my screen? So, they said that from what I have shown you so far, both from the circuit I drew and run with a multimeter, they said that the part which has the source voltage is always called the primary side. And the side that has the meter connected, or where you plug in your load, is called the secondary side of the transformer. And what is the basic thing influencing a transformer? Now, you see the formula. This is the basic formula for the mutual flux and the voltage of a transformer, the changing voltage of a transformer. Assuming the instantaneous voltage of a transformer, and this is the number of turns of this primary transformer that we've discussed so far, and is the rate at which the flux changes. The flux at that primary side changes. This is the number of flux at the primary side. So the voltage at that primary side is determined by the number of turns, change in flux of that primary side. And that being said, you convert this because in our first class, both technology, therapy, and P&O, we discussed that the rate of change of charge is called current. Are you following me? The rate of change of charge is called current. And in this case, the changing in flux is the current we are discussing, because we equally discussed that flux, just as it represents this thing. I think that was last week. That we said that flux is equals to current. That is the effect we are looking for. And what is pushing it is the voltage, which is the force, and inductance and resistance are the same. So for this one, the flux here, when we are discussing about electromagnetic principle, the flux here is the current, while the L, this L, which represents the number of turns, is the inductor value. The inductor value measured in Henry. The inductor value, that's the LP. The LP, the labor party we have, is the inductor value measured in Henry. Again, what is blank, Amarachi? So, in this case now, we said that the changing in voltage is equals to the number of inductor times the change in current over time. Are you following me? Change in current over time. Then, for the secondary side now, this is the mutual we are discussing about. This particular flux is the mutual flux. Let me shift this to this transformer here. Here, this is the primary side of the transformer, and this is the secondary side of the transformer. This is steel core, which we call the iron core transformer. And for this, the permeability is equal to 1, which means anything at the primary side is equals to what we get at the secondary side. There is no loss. Are you following? There is no loss. That's what is indicating. So in that case, what that is signifying is that the mutual flux, the one cutting the secondary side, is equal to the primary flux. The mutual flux is equals to the primary flux, where N is the number of turns of the secondary side. This NS is the number of turns of the secondary side, and phi P is the flux of the primary. While the second phi P is the flux of the primary side, while the mutual flux is the one cutting the secondary side, but they are equal. It's assumed that they are equal. So once we agree that this mutual flux is equal to the primary flux, we will now say that the secondary side of the transformer is equal to the number of turns of that transformer times change in the primary flux over time. Change in the primary flux over time. Then the K is the coefficient of coupling. The coupling effect of the transformer, which we call the coefficient of coupling, is the mutual flux over primary flux. And in this ion state equals to 1. The iron still is equals to 1. If you cannot see the screen, you should indicate on time. Is equals to 1. So it's equally agreed that the coefficient of coupling of a transformer can, and just like we know the power factor of reactive circuits, it cannot be greater than 1, but we have a limit. We have a limit which is 0.85. It cannot be lower than 0.85. The same thing applies to this. The same thing applies to this, but it is assumed that for iron steel, the coefficient of coupling is equals to 1. So say that as the lower the coefficient of coupling of a transformer, the loosely coupled, which means the voltage you have at the secondary side will lose. You will lose so much voltage at the secondary side. And this can cause a heating effect in the transformer. When what we are aiming to get at the secondary is being lost as heat, it can cause the transformer to heat up. And that causes some of the transformer hearing a humming sound, which means it's not coupled very well. Okay, Igweshi Israel Chukwudi asked us, an auto transformer have primary and secondary side? Yes, auto transformer have primary and secondary side, but selection matters. I think I need to show you, I'm going to show you the auto transformer symbol so that you understand what I mean. But just hold on, let's finalize this particular one. So assuming we have a coefficient of coupling that is less than 1, which means the mutual inductance are not equal to each other. So it means that the ES is equals to NS dot the phi M over the T is equals to NS the KOP. That is this coefficient of coupling times the primary side, using this first formula here. What is that coefficient of coupling formula? Hold on. This is my first time of trying to use YouTube. Hold on, let me look for what thing here. Okay, see what I'm looking for. This coefficient of coupling, which makes the mutual inductance to be equal to the primary side. Terry Thomas, I didn't get your question. You say, why does transformer have only secondary winding? Sir, why do transformer have only, have one secondary winding? Some transformers don't have one this thing or secondary winding. Can you people give me some minutes? Let me conclude and show you transformers so that you understand, please. Huh? Just calm down. So this is what I'm looking for. This is the coefficient of coupling. And when you take it to this, you will see that this mutual inductance is equals to change in a coefficient of coupling times primary flux. And that gives us our formula. These things are not necessary. All these formulas are not necessary because it's going to confuse you. What we are going to do is to check the transformer ratio, which is the alpha, determine the transformer impedance, which what we've done before. But this one is just to introduce you to some basic formulas so that when I come to class, our next class will be a physical class. When I come to class, you will not ask me a lot of questions. So let's solve an example. Let's say for the transformer in figure 2.21.3, this transformer, find the mutual inductance. Find the induced voltage EP if the flux phi p changes at the rate of 450 milliweber per second. 450 milliweber per second. Find induced voltage ES for the same rate of change indicated in part B. Then find the induced voltage EP and ES if the current IP changes at the rate of 0.2 amp per milliseconds. For A, we have the coefficient of coupling. This is it here, which is 0.6. The coupling, which is 0.6 times number of turns of primary, square root of L, number of the primary, times S, which is that of the number of turns at the secondary. This is it. Primary turns is 200 millihenry. The value is 200 millihenry. Then that of secondary is 800 millihenry. The rating. So when you multiply it, we have the mutual flux to be 240 millihenry. That is the mutual flux. Then for the primary voltage, we have 50 tons. 50 tons. Then we have 450 milliweber per second. So the primary voltage is 22.5 voltage. Then that of the secondary voltage. The secondary voltage will now be, we have number of turn 100 times K. This is the constant we are talking about, 0.6. 0.6 times 450 Weber. You can see that even though that this transformer is about 100 tons, instead of it to multiply this primary voltage by 2, you see that it lost a lot of voltage, which is why we are having 27 volts here. I'm going to do a recap of this thing in the class so that you understand one-on-one what I'm discussing. Then for the primary voltage again, we have LP dot P over the T, 200 millihenry, 0.2 amp meter per second. We are having 40 volts. Then when you do the same using the mutual flux, which is 240 times 200, we are having 48. which means we are losing a lot of energy. We are losing a lot of energy. So I think with this, we come to the end of class. If you have a question, you should put it on the platform. I'm going to attend to Terry Thomas' question. Terry Thomas, I'm going to share a screen for you to see other types of armor that we have. Okay, let me share another screen. Terry Thomas, this is for you. Who is this Calitech mobile solution? I think you are abusing the platform. You are abusing the platform. For this, you did not attend this class. Just know that and know peace. So Terry Thomas, let me share this screen for you. You asked for other transformers. Patrick, thank you so much. So can you see the screen I'm sharing? Terry, what is happening? Is the screen sharing? I think it's turning blank. Okay, it's up now. Can you see? Okay, Terry Thomas, this is talking about this transformer. This is the primary side of it. But at the secondary side, we have two secondary outputs. We call this one center tap transformer. Center tap. This is the transformer you can see easily in the market. The primary side, we have two wires. The secondary, we have three wires. We call it center tap transformer. It's just like the normal way the auto transformer works. So for auto transformers, what auto transformer will do is that from the primary side, this one will now be switching automatically, moving from one, like if this one, if we have another secondary coil here, this is 1, 2, 3, 4, 5, 6. It will be switching using relays to switch to secondary 1, secondary 2, secondary 3, secondary 4. Depending on the voltage level it wants to moderate, we use auto transformer majorly in stabilizers. Are you following me? Majorly in stabilizers. Depending on the voltage level you want to moderate, let's assume that as we are using 220 volts or 240 volts for all our appliances in the house, but what the utility company are supplying at the time, the one getting to your house, is at 180 volts, and your freezer or your television cannot operate, you have to buy stabilizer for it. Inside that stabilizer, there is an auto transformer inside it, and that auto transformer is designed in this way. It has different levels of secondary coils, and those different levels of secondary coil, maybe the first coil will be 10 coil, the second one will be 15, the third one 20, the following one 25, as the case may be. So what it will do is that if the voltage level is 120, and for it to correct to 220, it has to switch to secondary coil 3. So the work of that auto transformer is to sense the level of voltage at the primary volts and switch a relay that will correct it automatically. Did I make myself clear? Thomas, you should write. Ebere Edith, I bet you. The person that asked question is no longer replying. Terry Thomas. Okay, what I will do is that I will still edit this video and upload it. And I'm going to upload some other videos for you to come back and watch. Terry Thomas, did you get my explanation? I don't want to hear whether you are active or not. Okay. So this one, this transformer that we have here, the T transformer, is another type of transformer. So this transformer has two secondary outputs, but this time around is not center tapped. It's not center tapped. So this one has both positive and negative, different from what is here. The second one has positive and negative. You can see T4. This is T4, and T4 has one primary. The primary is 10. The secondary is 5, 5, 2, 1. That's the ratio of the transformer. 5, 5, 2, 1. What that means is that the primary has 10 tons of wire. The first secondary coil has 5. The second secondary coil has 5. The third secondary has 2. And the fourth secondary has 1. So you can see that this particular transformer has about 4 secondary coils, and you find this thing in advanced electrical equipment like the X-ray machines. There's what we call switching relays and transformers. I don't know how, if I still have that picture, I'll show you those transformers and how they are assembled. Let me for okay. Hold on, oh, let me look for it. If it's there in my phone, I will share it with you. Just hold on a bit. If it's not there, I will look for it because the transformer is one of the places I went to work. Well, it's not here. Okay. It is not here in this my phone, but I will look for it in my saved documents and send to you on the platform. So somebody asked a question. Terry Thomas, I think I've answered you. Chukwuebuka Miracle, thank you. Praise Ume said, I did not get you on what causes mutual inductance of a magnet. What causes mutual inductance is the magnetic flux. Praise Ume. Ume praise. Ume praise. Is she still online? Ume praise. Did you get what I said? I know you are here. Did you get what I said? Is there any other question I've not attended to? Is there any other question that I've not attended to? Thank you, Faith Annie. I've heard you, Kili Tech. So this class, as you know, a lot of people complain that they are engaged, some are in the hospital. That's why I have to put up this online class. The last time I had online class with technology class, it was about 3 times. So from time to time, we will try to see how we bring our classes online. The previous classes I had with these people, technology. The class was kind of hectic because we used the Zoom. At a time, it will stop. But the only problem we have here is that I can't hear you people respond to me. But the display and everything, they are all good. Huh? Can you understand me? Okay. So I hope you people have put up your raised numbers because I will still go through and mark your attendance. Huh? I will still go through and mark your attendance. Thank you so much. I will be ending the class soon. So you can go to your normal class. So thank you. I'll end the class. Take care. Wishing you all the best. And happy Valentine in arrears.